Do it again.
What we saw in the last video activity is that by looking at everyday phenomena like flight, we can start to make some informed deductions, in this case about the air and about whether it actually has substance. Observation and critical evaluation of experimental evidence are important skills to develop. Scientists also need to draw on models, theoretical descriptions of the world, to help them understand phenomena. In this band, we're going to look at one such model. It's called the particle model. And the particle model is fundamental to our understanding of everything in the world, including anything you might see in this kitchen here. Basically, the world is made up of three states of matter. There's liquids, like the water in this glass. There's solids, like this work surface. And there's gases, like the air around us. Now, what these three states of matter have in common is they're all made up of particles. They're all made up of lots and lots and lots of very, very small particles. However, each of these states of matter does have different properties. For example, the water in this jug here has a set volume, but it does flow. So I can pour this litre of water into another measuring jug, and lo and behold, I have a litre of water. So much for a liquid. What about a gas? Well, if I turn the gas on, the gas flows from the ring out into the room. And that's because a gas like a liquid will flow, but unlike a liquid, it doesn't have a fixed volume. It expands to fill the available space. On the other hand, a solid has very different properties. First of all, it has a fixed shape, it doesn't flow, and secondly, it has a fixed volume. Now, the common thing about these three states of matter is they're all made up of particles. Now, these particles are very, very small, about 10 to the minus 10 meters across. If I were to count the number of particles in this glass of water, there would be about 10 to the 25 particles. That's 10 million, 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 million particles. Now, the way we make sense of these different states of matter is to look at how the particles are arranged in each state. Water, like all matter, can exist in all three states: as a solid, like this ice, as water vapour, and as liquid water. In a solid like these ice cubes, the particles are in fixed positions. They're shown here in 2 dimensions, but you need to imagine a 3-dimensional array. In between the particles there's nothing, just empty space. You'll remember the properties of a solid, a fixed volume and a fixed shape. That's because the particles are in fixed positions and can't easily swap places with each other. That doesn't mean that the particles are static, they do vibrate, not just side to side, but in and out as well. The vigour of vibration can also change. Stop the tape here and note down why you think this change occurs. The answer has to do with how hot the solid is. As we heat up the solid, so the particles vibrate more energetically. So that's a solid. What about the properties of a liquid? When a solid changes into a liquid, as when ice melts, it occupies roughly the same volume. Therefore, the spacing of the particles must be roughly the same as in a solid. The difference is that the particles can now move around and past each other. It's exaggerated here to show how different the movement is. What's different between a solid and a liquid is that a liquid will flow. And I can use a simple analogy here. I can pour this rice, and as it pours, so the grains flow over and around each other, and they take up the new shape of the container. And the particles in water behave exactly the same way. As I pour it, they flow over and around each other, so they take up the new shape. A liquid then is different from a solid because it will flow. But like a solid, its volume is fixed. Although the particles can move around each other, they stay close together and can't break free and drift apart. What do you think will happen at the particle level if we heat up a liquid? As we heat up the water, we get a similar effect to that we notice with the solid. The particles move more quickly. If I leave this saucepan of water on the ring for too long, the liquid water starts to disappear. It's converted to the third state of matter, a gas. In a gas, the particles are much more widely separated than in liquids and solids. They move independently, occasionally colliding with each other. What gases also do is expand to fill their container. The space between the particles opens up as they freely move apart. And as we heat a gas up, so the average speed of the particles increases. So what happens if we mix two gases at two different temperatures, like the water vapour coming off this pan and the air around it? Here the hotter gas is the one on the right, where the particles are moving faster. When the barrier between them is removed, the particles start to collide with each other and their speeds begin to average out. The average speed ends up somewhere between the speeds of the two samples, as does the final temperature. So far we've looked at the differences between the three states of matter. Now we're going to look at what happens when one state of matter is transformed into another. Say, a solid going into a liquid, like when ice melts, or a liquid going into a gas. I want you to stop the tape for a moment and write down in your study file what you think happens at the particle level when a solid is converted into a liquid. Below 0 degrees Celsius, water exists in the solid state, ice. As it heats up, the particles in the solid vibrate more energetically about their positions. Eventually they vibrate so vigorously that they start to move from their fixed positions and jostle past each other to become the liquid state. This is melting, and for ice it occurs at the normal melting temperature, 0 degrees Celsius. The transition to a gas can occur at any temperature. For example, puddles dry up even on the coldest of days. What's interesting is that evaporation doesn't just occur from the surface of liquids, it also occurs from the surface of solids. In a liquid, what happens is that the particles are moving around at a range of speeds. Every so often, one of the particles at the surface is moving fast enough and has enough energy to escape from the liquid state to go into the gaseous state. The hotter the liquid, the faster the particles move around, and thus the more likely they are to break free. So as we heat up the water, evaporation occurs more readily. Eventually the transition from a liquid to a gas occurs so readily that gas bubbles form in the liquid. This is boiling, and for water at atmospheric pressure it occurs at 100 degrees Celsius. Of course the whole process can happen in reverse. For example, the water vapour here is condensing on the cold tiles to give us liquid water. I could take this liquid water and put it in a freezer to give me solid ice. As a last activity for this band, I want you to write down in your study file what you think happens at the particle level as we cool down a gas to give a liquid, and then cool it further to give a solid.
Welcome to the show. I'm going to talk to you about gases, and in particular I'm going to talk to you about the gases in the air itself. Now the air is a strange and rather wonderful thing. Can't see it, can't touch it, can't smell it, it's all around us. Can feel it, just about, on a windy day. But if you get it very, very cold, then you can make it turn into a liquid. And liquid, very different thing indeed. Let's have a look. The air split into two of its components: nitrogen, oxygen. 20% oxygen, 80% nitrogen. If I spill some, it evaporates almost instantly and goes back into the air where it came from. Oxygen is blue. So now we can see it. We can touch it. We can wash our hands in it. Can't smell it. Much the same, no smell. What about taste? Well, let's see. Bit of oxygen. Yeah, still can't taste it.
So far, we've discussed the air quite generally, deciding whether it has substance or not, and then looking in detail at its properties as a gas. In this part of the video, we're going to look in detail at the actual chemical composition of the air. Somewhere like this British oxygen plant is a good place to start. What they do here is break the air down into its component gases, and then sell them on for use in different industrial processes. How they do this is to cool the air down and then apply pressure.
The first thing that's formed when we've cooled the air down is a liquid that has the three main components in it: nitrogen, oxygen and argon. We then have to use the distillation column to separate those constituent parts out, using the fact that they boil at different temperatures and have different densities.
To get an idea of how cold these liquids are, oxygen has a boiling temperature of -183, argon -186, and nitrogen -196 degrees Celsius.
How do we get liquid air? Well, really what we have to do is first of all get the air very cold. And I can do that by actually pouring a bit of liquid nitrogen into this brass tube. Nitrogen is a very, very cold gas as a liquid, and in fact is slightly colder than the condensing point of air. So if we just let that sit for a little bit while it cools down, I can show you a phenomenon. Let's just have a look at the room which we're surrounded by. This is full of air, and in fact I measured it and it comes up to about 2,000 cubic meters of air. The weight of that is about 2.5 tons. So just in this room there's 2.5 tons of air. I suppose that we were to actually cool this down, so we turned it into a liquid, one gas at a time as it trickled down. What will we actually get? Well, first of all, the nitrogen, which is the largest component of the atmosphere, 80% of it, would just about fill that pond. And the oxygen, which is about 20% of the atmosphere, a little bit more than that, would fill that pond. The next gas I want to think about is argon. That's about 1% of the atmosphere. And if we condensed all of that down to liquid argon, it would actually just about fill this cardboard archive box. And carbon dioxide, another gas, quite small proportions, 3/4 of a litre of that, and the carbon dioxide will be about the size of a video. Now we start getting down to the inerts, or the noble gases. Neon, 25 millilitres, about the size of one of these batteries. And the helium, which is still present in the atmosphere, although not used from the atmosphere, would just about be the volume of that copper-coloured bit on top of it. Now, what about the very rare gases? What about our krypton and xenon? Krypton, from all of the gas in this atrium, would just about fill this little vial. And the xenon would just about occupy the blue powder which I have at the bottom of it. Now let's move back to this little experiment. You can see that we've now got a liquid dripping off the outside of this copper tube. Now what is it? Well, we have liquid nitrogen inside, and liquid nitrogen is so cold that the air on the outside of the tube is condensing. It's milky white because it contains CO2 and a little bit of ice, of course, from the moisture in the air around us. But nonetheless, that is liquid air. And I have to tell you that there is nowhere on the surface of the Earth which is cold enough to cause the air to condense.
The effect of the enormous shell of air that surrounds the Earth, the atmosphere, is in fact to warm the planet up. Without it, the global mean surface temperature would be about 30 degrees Celsius colder. Closer to the surface, the air is densest. The higher you climb, the thinner the air gets. That's why mountaineers get more breathless at higher altitudes.
So what do we have to say about oxygen? Oxygen is blue. And how can we tell it's oxygen? Well, we know that it relights a glowing splint. So I get a splint, blow it out and make it glow, put it in oxygen, standard classic test for oxygen. The applications of oxygen is really one of the oldest of the industrial gases to be used. Its main application, of course, is in steel making, and it is still probably the largest single slice of oxygen use. It's a reactive gas, and as a reactive gas, that makes it very, very useful indeed.
Oxygen actually improves the efficiency of burning. Here, the flame is made much hotter by adding pure oxygen. Temperatures of up to 1300 degrees Celsius are being achieved. This intense flame can be used to cut out templates from metal up to 12 inches thick.
Things which burn reasonably well in air burn an awful lot better in oxygen because there's a lot more of it. You've already seen it relighting a glowing splint. But what about things which we don't really think of as burnable at all? I've got here some steel wool. If I take a small piece of steel wool, soak it in liquid oxygen, then set fire to it, what do you think is going to happen? Well, now you can see that that's burning very, very intensely indeed. In fact, it's one of the hottest flames known, and the fuel is steel.
In the same way, these iron rods are the fuel in this thermal lance. Using an oxyacetylene torch, they are heated until they reach their melting temperature, and pure oxygen is then added. The iron rods are literally burning. They are reacting with the pure oxygen to form iron oxide, and in this process are giving off enormous amounts of heat. Lances are capable of melting almost anything, including concrete and steel. In fact, the only material they can't efficiently penetrate is carbon.
But oxygen is only one component of the air. There are others. But the largest component of all is nitrogen. Now there's oxygen, blue, and there's nitrogen, which is clear. The test for oxygen, if you like, is that it will relight a glowing splint. Glowing splint, and I think that's a pretty positive test. What happens if you put it into nitrogen? The splint goes out. This is a dead gas. It does not support combustion. We can't breathe it and make use of it as such, but nitrogen is an essential part of proteins and in fact of our whole body metabolism. And so though we don't directly get it from the atmosphere, other things have to do that for us. Without it, we couldn't exist.
Lightning is one such mechanism, able to convert gaseous nitrogen into a more accessible form. Special bacteria in the soil also achieve this. But apart from these processes, nitrogen is on the whole reluctant to take part in reactions.
The lack of reactivity of nitrogen is also an important industrial aspect of the gas. For example, it'll put a fire out relatively easily. And so many of its uses are centered on blanketing. This is really to exclude oxygen or other oxidants, but usually it's oxygen, and it goes on top of things like oil tanks and a whole variety of areas.
Oxygen and nitrogen actually make up almost 99% of the Earth's atmosphere. The remaining 1% consists of carbon dioxide, argon and other rare gases, and a variable amount of water vapour. This water vapour exists in the atmosphere as part of the water cycle. As water evaporates into the atmosphere, it rises, and as it rises, it cools down and condenses to form clouds. What happens next is precipitation, as rain or snow. The amount of water in the air differs markedly in different environments. In a desert, it's very dry. In a tropical rainforest, it feels noticeably damp and humid because of the much higher water content in the air. Most of the remaining gases in the air are known as the noble gases. Noble because they won't react with other substances. The most common of these is argon, which is extracted on an industrial scale.
The role of argon in welding of aluminium provides a gas which doesn't react with the molten metal. Aluminium is very, very keen to form an oxide, and if you can put a shield of inert gas around it, then you can prevent the oxide forming, and that way you can get a good join. One of the noble gases is helium. There's only quite a small proportion of it in the atmosphere, and it's still quite a widely used industrial gas, although of course it isn't taken from the atmosphere itself. The other ones are much rarer, and one would think that neon and krypton and xenon were perhaps not such important gases. And yet, strangely, neon, of course, we all know what a neon sign looks like with its lovely glow, but neon is also the exciter in the fluorescent tubes which we have in our home, or in this case, the tubes are coated with phosphors on the inside, which makes them glow white. Krypton and xenon. I think the krypton light and the halogen light on our cars and things of that sort was perhaps the first exposure that we had to the uses of those types of gases.
Finally, a more familiar, though lesser component of the air, carbon dioxide.
Now behind me, you can see cold vapour spilling down. This is actually done with another gas, and that's CO2. And that actually doesn't form a liquid at atmospheric pressure, it only forms a solid, known as dry ice. Carbon dioxide normally goes from a solid straight to a gas. But if you put it under pressure, it can also form a liquid. Liquid carbon dioxide is an extremely good agent for dissolving fats and a number of other chemicals as well. And in fact, it's used for decaffeinating coffee. The coffee beans are exposed to liquid CO2 at high pressure, the caffeine dissolves in the CO2, then the bean comes out, the CO2 evaporates away, and you have decaffeinated coffee.
So the air is a mixture of these different gases. At the particle level, the air consists of nitrogen particles, oxygen, argon, carbon dioxide and water particles, all mixed together in appropriate quantities. Now, each of these gases has its own set of properties. And when we mix them together, the air has properties which reflect the properties of each of the individual gases, although it's modified to some extent. For example, some things burn really vigorously in pure oxygen, but when we burn them in air, they only burn gently.